Maximum Product Subarray. Here's a question that separates the good from the great. Maximum Product Subarray looks easy, until you hit those negative numbers and zeros. This Pattern Mastery 100 staple pops up at companies like Google and Amazon, and it's famous for tripping up even seasoned coders. If you can nail this one, you'll show interviewers that you're not just following patterns, you truly understand array dynamics and edge case thinking. Let's unlock the secret together. Let's break down the challenge. Given an integer array, your job is to find the contiguous subarray that has the largest product. Unlike some problems, multiplying negatives can flip the result, and zeros reset your progress. That's why this problem is sneakier than it seems. Now let's assess our options. A brute force approach would try every subarray and compute the product, on squared or worse, but we want on time. The trick is to keep track of both the maximum and minimum products ending at each index, because a negative number could turn your lowest product into the new maximum if multiplied. As we scan, we update both, and always check for zeros that reset the product chain. Here's the structure of our solution. First, initialize 3 variables. Max_prod for the global max. Cur_max for the current maximum product ending here. Cur_min for the current minimum, for handling negatives. Then, start all at the first element. Next, for each number in the array, starting from index 1. If the number is negative, swap current maximum and current minimum. Update current maximum as the higher of the number itself or number times current maximum. Update current minimum as the lower of the number itself or number times current minimum. Update maximum product if current maximum is greater. And lastly, return maximum product.
Let's try to implement it using solution 1. We start by defining a class named solution. This simply organizes our function inside a neat container. This creates our function maxProduct, which takes a list of integers and returns the largest possible product of a contiguous subarray. Here we store the length of the list in n so we don't have to calculate it multiple times. We create a list called maxDP, filled with zeros. MaxDPI will keep track of the maximum product ending at index I, and we do the same for minDP, which tracks the minimum product ending at index I. This is important because a negative number can flip a small negative product into a large positive one. We initialize both the max and min product at index 0 to the first number. This sets our starting point. We also set our global result to the first number. This will keep track of the best product we've seen so far. Now we loop through the array starting from index 1. This single pass takes on time. We check whether the current number is non-negative. If it's positive or 0, multiplying it keeps the sign stable. For positive numbers, the new maximum product is either the number itself or the product of that number with the previous maximum. We choose whichever is larger. Similarly, the minimum product is either the number itself or the previous minimum times the current number. When the number is negative, multiplying flips signs, so everything reverses. Now the new maximum might actually come from the previous minimum multiplied by this negative number, and the new minimum may come from the previous maximum multiplied by the negative number. We update the global result if the new max product is larger than anything we've seen so far. Finally, we return the largest product found across the entire array. And that's how this algorithm works. It first sets up 2 trackers to monitor the highest and lowest running products, then updates them in a single pass to account for positive and negative swings. Efficient, simple, and elegant. Check. Let's walk through this test case for the maximum product subarray and see why the result is correct. Input is nums equals 2 3 negative 2 4. Each number represents part of a continuous sequence, and we're looking for the largest product from any contiguous subarray. Our algorithm keeps track of both the current maximum product, the best positive stretch so far, and the current minimum product, the most negative stretch, which becomes useful if we hit another negative. Step by step. Start at 2. Current max equals 2, current min equals 2, best answer equals 2. Move to 3. Best contiguous product so far is 2 times 3 equals 6. Current max equals 6, current min equals 3, answer equals 6. Move to negative 2. The negative flips signs, so we consider how it affects both max and min. From 6 and 3, multiplying by negative 2 gives candidates like negative 12 and negative 6. New current max becomes negative 2, current min becomes negative 12. Best overall answer remains 6. Move to 4. Candidates are 4, -2 times 4 equals -8, and -12 times 4 equals -48. Current max becomes 4, still not beating our global best of 6. So the maximum product of any contiguous subarray is 2 times 3 equals 6. The output is 6, and the expected value is also 6. Everything lines up perfectly, showing the solution works as intended. Now let's try another implement approach using solution 2. We begin by creating a class named solution, just a container that holds our function. This defines our function maxProduct, which takes a list of integers and returns the largest product you can get from any continuous chunk of the array. We set curmax to the first number in the list. This represents the highest product we can achieve ending at the current index. And we also track curmin, the smallest product ending at the current index. This is crucial because a negative number can turn a small negative product into a large positive one. We initialize result as the first value. This variable will always hold the best product we've seen so far. Now we loop through the rest of the numbers, starting from index 1. This loop touches each element once, on time. This checks if the current number is negative. If it is, multiplying flips signs, meaning the current max could suddenly become a min, and vice versa. So when we see a negative number, we swap them. It's like saying, because the sign flips, what used to be my best might now become my worst. Swap the roles. We update the running maximum product. Either start fresh with the current number, or multiply it with the previous running max. We choose whichever gives a bigger value. Similarly, we update the running minimum product. Either the number itself, or the previous running min times the current number. We pick whichever is smaller. We compare the updated running max with the global best result found so far. If it's larger, we update our result. This becomes the new maximum product. Finally, we return the maximum product we found across the entire list. And that's how this algorithm works. It first sets up running max and min trackers, then updates them in a single pass while handling sign flips from negative numbers. Efficient, simple, and elegant. Check. Time to validate this test case for the maximum product subarray, especially interesting because it includes a 0 and negative numbers. Here's the input. Nums equals -2 0 -1. We track both the current max product and min product because multiplying by negatives can flip the values. Start with -2. Max prod equals -2. Min prod equals -2. Answer equals -2. Next value is 0. Any product involving 0 becomes 0. Reset. Max prod equals 0. Min prod equals 0. Update answer. Now answer equals 0 because 0 greater than -2. Next value is -1. Candidates. -1, 0 times -1 equals 0. Max prod equals 0. Min prod equals -1. The answer stays 0 because the best we've seen is still 0. The presence of 0 effectively breaks the subarray, and none of the segments produce a positive product larger than 0. The output 0 matches the expected 0, confirming the algorithm handles negatives and zeros exactly as intended.
Let's have a quick recap. Breakdown recap. This problem challenges us to find the contiguous subarray that produces the largest product. What makes it tricky is that negatives and zeros completely change the game. One negative can flip a loss into a win, while a 0 can reset everything. The task is less about simple multiplication and more about managing unpredictable swings in sign and value. Assess recap. We started by comparing approaches. A brute force method that checks every subarray is too slow to scale. The key insight is recognizing that a negative number can turn a previous minimum into a new maximum. By keeping track of both the current max and min at each step, we can handle those sign flips dynamically and efficiently in a single pass. Structure recap. Our logic revolves around 3 values: the global maximum product, the current maximum, and the current minimum. As we move through the array, if we hit a negative, we swap the current max and min before updating them. Each new number becomes a decision point. Do we start over or multiply to extend the existing chain? Implement recap. When we implemented the logic, the process flowed smoothly. At every step, we updated our running max and min products, handled sign reversals, and kept a record of the global maximum as it evolved. Conceptually, it felt like walking through the array with real-time recalibration, adjusting to every twist caused by negatives and zeros. Check recap. Testing confirmed the approach works perfectly. In our example, The product chain resets correctly at 0 and captures the best possible result. 2. Even with more complex inputs, the algorithm consistently identifies the strongest contiguous product in ON time and constant space. The big takeaway here is adaptability. The maximum product subarray teaches you that in algorithmic thinking, just like in problem solving, your approach must adjust to changing conditions. It's not just about finding the maximum. It's about managing uncertainty efficiently and confidently.